Well, here we are once again at the physics video lecture. It's Physics 107B video lecture 11. So we're in the chapter on waves, and I couldn't see whether I had assigned a certain set of problems already, so I'm going to put them up here on the board right at the beginning so as not to forget. We'll see. I didn't find these. I was looking at the lectures again. So here we are in chapter 9, and we're looking at problems 3, 4, 7, 13, 33, and 35 for starters. But what I want to do now is talk about electromagnetic waves in matter, and just to go through the laws of reflection and refraction that we know of Snell's law, and see how we get those with the wave theory. So, electromagnetic waves in matter. Since the electromagnetic waves travel with the speed of light, we assume they should fulfill all the laws of optics that we already know. So we'll start with Maxwell's equations in matter with no currents. Equations in matter. So these are what we had. So no free charges, no currents. We had talked about these earlier, and now we're going to use them. So we have the divergence of the displacement vector vanishing, of course, magnetic field vector divergence vanishing, curl of E minus dV dt. We have the same form there, but the curl of H is equal to d displacement with respect to time. So of course we have too many quantities here, but we have a linear medium. In a linear medium, we have these relations. The displacement is proportional to the electric field, and H is also proportional to the B field. So we can go ahead and plug these in. In fact, I could do that right here. This, we've got direct proportionality. We have a 0 on the right side, so we just end up with divergence of E vanishing. Nothing changes on the magnetic field. Faraday doesn't change either. But these two relations put together give us curl of B equals, right? We have the E over mu, so that's divided by mu. That's going to cross multiply over D. So we have an epsilon mu, and d E dt. Okay. So what's interesting is we're looking at exactly the same form of Maxwell's equations as we had in vacuum, but now we have these material dependent properties. And they're nicely named because in vacuum we have epsilon naught and mu naught. Okay. So that means we inherit everything we had before, and we can go right to work with it. Note that now our wave speed is no longer the speed of light in vacuum, but it has the same form, 1 over root epsilon u. And we can expand that to 1 over root epsilon naught u naught epsilon naught u naught over epsilon u. And so this is going to be n, and this, this is going to be c, 1 over speed of light in vacuum, and this is going to be 1 over n, okay? So this is what we'll call the index of refraction. It's going to be greater than 1, and the speed of the wave in matter is less than or equal to the speed of light in vacuum. So yeah, we'll just use V now instead of C. Good. So having done this, we have to remind ourselves of the boundary conditions. So now we're looking at the waves at the boundary between two media that will be characterized by this quantity n here, the index. So at the boundary of two media, this is the one we always do in optics, and our boundary conditions for the perpendicular components, for the E field, B field, perpendicular components. And then we have parallel components parallel components are equal E2 parallel, and the parallel components of the B field look like this. So we had that a little while ago. And now we just have to write down the same E and B that we had the other day, remembering our picture, you know, X, Y, Z. We had E like this, and so forth. So just reminding of these expressions, and I'm going to write down the formulas for them in a minute, right? We've got the perpendicular transverse waves, E and B. So I can fit them here. Let's go ahead. So we have, and this is what we'll use for the duration. We've got E0 K dot R minus omega T, dot product. And n hat is the direction of propagation. B in fact, I'm going to skip that. It can just be written as K cross E. So this is useful. We've just got the cross product of the direction of propagation with the E field giving us B field, just as up in this picture here. And I'm just going to use the complex form and not worry about whether I've got a tilde on there or not. Okay, obviously it's the real part, but this is much more convenient to work with. Okay, so we'll keep the complex form there. And now let's go straight to the situation in optics that we're interested in. So optics, we have, and I'll label this picture to be big enough. This will do. We're going to have our z-axis, our x-axis, so our y-axis is coming straight out of the board. And we're going to call this the one side, and this is the number 2 side. We have a ray, actually not a ray, a wave vector coming in, say like this, and there is a reflected and a transmitted wave. So these are the wave vectors. Let's make this one a little straighter. Okay. So the construction is just like ray optics because of these vectors here, wave vectors. So what do we have here? We have theta incident, theta reflected, theta transmitted, and we have, here I'll use a different color, K incident, K reflected, and K transmitted. Okay. And we have these boundary conditions. So everything is actually up there that we need. And I don't have to write all of these down. Let's see. Ah, yes. This is V as defined up there. Right up there. Okay. So we have E and B twice on the left side because they add up to the total field on the left side here. And then we have E and B once on the right side, adding up to the total field on the right side. So I think I'll write them all down. So we have for the incident electric field this constant, and then e to the I k dot r minus omega t. It's always going to be the same thing, labeled with incident and so forth. And then B incident, I'm not going to write all of them down. But on the one side, that's V sub 1 K cross E incident. So we're going to have the same thing for the reflected and the transmitted waves. So same for reflected and transmitted. And they all have the same frequency. That's really important because the frequency wave number relation holds true in all of these. So the really important point here is for all of these fields, got same omega, so K incident, V incident, and V incident, of course, is V1, since it's on the one side there. Okay. And K reflected, V1, and K transmitted, V2. So those relations all hold. So on the reflected side, it's going to be the same wave speed. On the transmitted side, same frequency, but wave number times different wave speed. That's actually what's going to give us this different angle here when we go through with the calculation. So yeah, this is crucial. Good. So yeah, on the left side, we will add these two, and based on the boundary conditions, they'll be equal on the right side. So we'll have reflected plus incident plus reflected on the left side equals transmitted on the right side. So writing those out, we always have the same basic boundary condition. I'll go ahead and leave those out. They're all going to be of the following form. Now, the boundary is at z equals 0. Okay. At z equals 0. So we have something on the incident side, e to the I k incident dot r minus omega t, plus reflected k reflected dot r minus omega t running out of room equals transmitted, and we're just filling in the names of these fields. Okay, e to the I k transmitted dot r minus omega t. So obviously the e to the minus I omega t cancels from the whole thing, and this is at z equals 0. So what we have here is k times r in the xy plane. Okay, we've got the k as shown here dotted into r in the xy plane. So let's go ahead and see what that gives us. At z equals 0, we have k incident dotted into, I'll just write r sub xy equals k reflected dotted into r sub xy equals k transmitted dotted into r xy. Okay. Now we haven't said anything yet about where these vectors actually lie, but these equations are going to tell us that they're coplanar. Because these are three equations. I can have ki minus kr dotted into this vector, ki, kt dotted into this vector. Okay. And since r is in the xy plane, xy plane and y is coming out of the board here, we're going to have k I k r k transmitted or coplanar. from that, we can go ahead and choose it to be the y=0 plane, which then gives us what we have in our, in our picture up here on the board. So, good. Good, well, we've used this now. Assume y=0. Now we actually have this exact picture up here. We have K incident. Now it's just the x component. Okay. Yeah. So literally this picture now. Okay. So K's only have their x components and their z components. So K incident x equals K reflected x component. We immediately get sine theta incident equals sine theta reflected. Okay. Those x components, those are the ones that are pointing up there. So there's our law of reflection. Reflection. And then we're going to do the transmission, and now we don't have that equality. Now we have from K incident x component equals K transmitted x component, but the fact that the speeds are different on each side, remember omega was constant, and we had V, we had these relations right here. So now we get K incident sine theta incident equals K transmitted sine theta transmitted. And I can go ahead and divide that sine theta incident, the K transmitted over the K incident is just equal to, write that first, transmitted. So K transmitted over K incident is just equal to V1 over V2. Okay, let me open up some space here. Sine theta incident equals V1 over V2 sine theta transmitted incident. And remember, N, so we had V was equal to C over N. So N is equal to C divided by V. And so cross multiply here and replace the V's by the N's, then you get N1 sine theta incident equals N2 sine theta transmitted. And that was what we set out to find. Okay. Right, so V2 sine theta incident, but we divided by V1, we would have N over C. Yeah. So yeah, that's Snell's law. So law of reflection, Snell's law, law of refraction, that's what we set out to find today. Let's see where we're going to take this. Yeah, the next thing I want to do is reflection and transmission. So next what we're going to do is reflection and transmission coefficients. Right now we just have these geometrical relations for reflected and transmitted waves, but we do not yet have the intensities. Okay. So next we want the intensities of reflected and transmitted waves. Next, reflection and transmission coefficients. Good. Let's see here. We're going to save that for next time. Okay, see you guys next time.